Hi everyone, in this video I'd like to talk about interesting sigma-algebras, important examples of sigma-algebras and probability spaces that are built from them. The definition first. So suppose that I have a sample space omega and I have a sigma algebra on it and a probability measure on that sigma algebra. So that's a set omega, sample space. This one will be a sigma algebra. And this one will be a probability measure. And then such a triplet, so a triplet like this, is called a probability space. Okay, so in order to do probability or stochastic processes or any kind of probabilistic statements, we always need a sample space, we always need a sigma algebra, and we need a probability measure. Okay, the elements of the sigma algebra, if a set A is in the sigma algebra, then we say that A is measurable. It's a measurable set or just measurable. And in a probabilistic language you would call an event. So the measurable sets are the events. Okay? Those are the subsets of the sample space which belong to the sigma algebra and therefore which you can plug in a probability. It makes sense to talk about the probability of an event. Why? Because A is an event, means it's in the sigma algebra. The probability is a set function from the sigma algebra to real numbers, so you can actually feed the probability with an event A, with a measurable set A. Okay? So B of A makes sense in this construction. Okay, so what I want to do next is examples, several examples. The first example I want to tell you about is a very simple one. F star, which has the empty set and it has omega. If you go back to the definition of a sigma algebra, you easily convince yourself that these two have to be in a sigma algebra. Omega by definition, and if you take the complement of omega you get the empty set. And it's also easy to convince yourself that if you have these two in your sigma algebra, then it actually satisfies all the properties we need. This is called the trivial sigma algebra. Trivial sigma algebra. It has no interesting events in there. It has the null event and all of the sample space and nothing else. So in this probability space, where you take the sigma algebra to be a trivial sigma algebra, there is not much to talk about. Actually, there are no interesting events in here. Okay? Now, here is another example. If omega happens to be countable, so you can list its elements, then almost always people take the power set of omega for the sigma algebra. So all subsets. Okay, and if omega is countable, then this is a good choice. It's easy to build a probability measure on this sigma algebra. There are no problems, no issues. So often that's the natural choice and that's what people make. For example, if you keep rolling a die and you're interested in how many rolls do you need until the first time you see 6, then this is a countable state space, and then all subsets of this state space will form a sigma algebra. So for example, you can ask questions about what's the probability that you need to roll between 5 and 8 times to see 6 the first time. Okay, and that's gonna be in the power set, is the discrete interval 5 to 8. Okay, so that was another example. Here is the next example. Suppose that we have again a sample space and take any proper subset of omega so this is not empty and it's not omega, it's a proper subset, then you can do something called the sigma algebra generated by A by including the empty set, which is easy to see, it always has to be in. Let's include the set A, then because of the properties its complement needs to be included, and then because of the complement of the empty set, or actually because of the defining properties, omega has to be included, and nothing else is needed. So this is a simple sigma algebra. It has 4 elements: the empty set, the subset A, its complement, and omega. This is the sigma algebra generated by the event A. Sigma algebra generated by this single event A. Okay, that's another example. It's quite simple in a probability space. It's quite simple. The only interesting event you have is A and not A. It's still not completely trivial, but it's quite simple. Okay, so these were a few examples which are important. Let me now give you a lemma which will be useful to come up with more examples, and actually we're going to use that lemma in a second. Okay, so here's a little lemma. Suppose that you have a family, which I call script E, of subsets of omega, so a family in the power set. Okay, so there's a family of subsets. Then there exists a smallest algebra that contains all sets in script E. That's a lemma. There is a smallest algebra that makes this family of subsets an algebra. Okay, this family of subsets could be anything. Maybe the intersections, unions don't belong to this family. It doesn't need to be an algebra. There is a smallest algebra that contains this script E, which is an algebra. And it's actually 2 statements at once. Then there is a smallest sigma algebra as well. Okay, so I'm abbreviating 2 lemmas at once. Lemma 1 is that for any family as a subset of the power set, any family of subsets of omega, there exists a smallest algebra that contains it, and then there also exists a smallest sigma algebra that contains it. And I'm not going to prove this, but the way to do it is just look at all algebras and intersect them, or look at all sigma algebras and intersect them, and this is how one constructs this thing in a nutshell. These are called, so either the algebra in the first statement or the sigma algebra in the second statement are called the algebra or the sigma algebra generated by the family script E. So if you have a collection of sets, collection of subsets, then you can have a sigma algebra or an algebra generated by that collection. And for example, if you have just a singleton in your collection, so E just contains A, then this is going to be the sigma algebra generated by A. It's actually an algebra as well, because it only has finitely many things in there. Okay, so that was the little lemma. And this lemma will be very useful for us in a moment, because now what I want to do is I want to show you a very important example, and here is how it goes. So again, an example, but this is going to be a very important one. So it's not just an illustrative example, it's actually something everybody uses. So let me define a family of subsets of the real interval. So it's going to be of the following form, union from 1 through n of ai, bi's, where these are intervals. So A and B will be real numbers in a second. I'm going to write this out explicitly, but I'm going to take first I'm going to try to show you the top of the page as well. Okay, so I'm going to take real numbers AI and BI. I'm going to take intervals which are open on the left, closed on the right, and then take unions of these, finite unions. So I'm going to take these kind of finite unions where n is an integer, finite integer, okay? A1 is a real number except it can be minus infinite as well. So A1 is a real number, it can be minus infinite as well, okay? Then Bn is a real number, or it can be plus infinite as well. So the first interval on the left could go out to infinity, and the last interval to the right could go out to infinity. Otherwise, these numbers are increasing and reals. So A1 is less than B1, which is less than or equal to A2, which is less than B2, less than or equal to A3, less than B3, and so on and so on. And then less than or equal to AN, which is less than BN. And so A2 to AN are real numbers, and B1 through Bn minus 1 are real numbers. Okay, so this is a little bit complicated if we write out everything, but it's actually simple. I'm just claiming that you have these intervals open on the left, closed on the right, and you take a finite union of them. That's what it is. Except that the first interval can go down to negative infinity possibly, and the last interval possibly can go up to positive infinity. Okay? This set, you convince yourself that this thing is an algebra. Okay? You convince yourself that if you take two finite unions like this and you do the union of these two finite unions, it's still a finite union of this form. Okay? And you also convince yourself that R is included. So the set, just a remark here which I didn't tell you explicitly, the set is actually R. Okay, so this is an algebra on R. Okay, now the point is that this is not a sigma algebra. So here is an important and an interesting feature. This is not a sigma algebra. Okay, why is this not a sigma algebra? Well, it's just a matter of showing an example where a countable union is not included in A. Okay, and here is my countable union. Take intervals of the form 0 and 1 minus 1 over n. Open on the left, close on the right. Okay, take the union of these for all n's. Now, as n increases, 1 over n decreases, 1 minus 1 over n increases, so this is an increasing system, an increasing sequence of sets. Okay, the union is actually its limit. And where is it increasing up to? Well, anything strictly between 0 and 1 will eventually be swallowed by these. So the infinite union contains anything strictly between 0 and 1. However, it does not contain the number 1. The right end number 1 is actually not in any of these things, so it's not in the union. So when you do this infinite union, it is going to be the open interval on both ends, 0, 1. Okay? And this guy here is not in the algebra A. There is no way to cook up the open interval 0, 1 from finite unions which are closed on the right. Okay, so that's an example showing that if I take algebra events, these are all belonging to the algebra A, I take an infinite union of them, what I get is not in the algebra. So therefore this A, script A, is not a sigma algebra. But then I can make a definition. Namely, I take this algebra A here, which is not a sigma algebra, and I'm going to generate a sigma algebra out of this. So BR is called the Borel sigma algebra. On R, okay, and this guy is defined to be the sigma algebra generated by A. So if you remember from the previous page, you had this little lemma that said you can generate, if you have a subset, a collection of subsets, you can generate a sigma algebra from there. That's exactly what we're doing here. So generate the sigma algebra from A, sigma algebra generated by the script A algebra. Okay, this is script A. Maybe I should try to make it nicer. Okay, generate the sigma algebra from script A, and that's what we call a Borel sigma algebra. Okay, now here is a fact. Again, this is just a very brief kind of mentioning of some notions in measure theory, so I'm not proving these things. But here's a fact. Almost every interesting subset of R you can come up with, almost anything you can come up with, will be contained in the Borel sigma algebra. Okay, so intervals, open or closed intervals will be contained. The open interval 0, 1 is going to be a member of the Borel sigma algebra, as you can see, because you essentially just extend as a limit of these things, and you get the open interval 0, 1. Singletons will be in the Borel sigma algebra. Almost anything you can come up with in your mind will be a member of this Borel sigma algebra. It's not easy to find subsets of R which are not measurable, which are not in the Borel sigma algebra. Okay, those interested can look up the so-called Vitali sets, which are about this phenomena. So how to construct something that's not Borel measurable, that's not in the Borel sigma algebra. Okay, now let me just generalize all this construction very briefly and show you how to build up more complex and more interesting examples starting from the one-dimensional Borel sigma algebra. So what you can do is look at similar constructions, and I'm not going to go into much details again because this is not a measure theory unit. You can define R to the n, a sigma algebra on R to the n, namely the n-dimensional real linear space, by doing the sigma algebra generated by rectangles, finite unions of rectangles. Okay, so what is a rectangle? In R2, for example, if you look at R2, you can look at intervals of the form we considered before, so open on the left, closed on the right, and then do the same here, open on the left, closed on the right, and then you can have these kind of rectangles which include the upper right boundaries but not the lower left boundaries, and then you can take finite unions of these, then you can generate the sigma algebra by these finite unions, and that's the Borel sigma algebra on the n-dimensional space. Okay, then you can go further than this. You can actually generate the Borel sigma algebra on infinite dimensions. What is R to the infinity? Well, these are sequences, right? Infinite sequences of numbers. A sequence, if you want, is just an infinite dimensional vector, right? How do you do that? Well, what you do is you generate the sigma algebra of finite cylinder sets. You look at the sigma algebras. Okay, you look at the sigma algebra of generated by finite cylinder sets. In other words, you look at the infinite sequence and you say, I want to fix rectangles for the first n members of my sequence. So I want to say that A1 is between 1 and 2, A2 is between 5 and 8, A3 is between 10 and 11, and then everything else is free. That's a cylinder set. The sigma algebra generated by all these is going to be the sigma algebra on R to the infinity, sigma algebra on the sequences. Again, almost anything you can come up with is going to be in that Borel sigma algebra. Okay, so this contains, all these contains all interesting sets. For example, this contains a lot of interesting things. For example, all the sequences which have a limit. That's a subset of the set of sequences. It is going to be Borel measurable. So you can ask yourself, what is the probability in some probability space, which you define on this, of a limit existing. It also contains all the sequences where the supremum of the sequence is larger than 5, as an example. It contains all the sequences when the lim-inf of the sequence is larger than 5. So again, practically anything you can imagine without going into much details. Anything that comes up in everyday life, almost anything that comes up in everyday life, is actually going to be measurable according to this sigma algebra. Okay? And then you can actually go further than this. You can even define the Borel sigma algebras on functions. So far we had sequences. What is a sequence? Well, you index real numbers with integers, so x1, x2, x3, and so on and so on. You can also index real numbers with a continuous set T, for example, R again. So this thing is a continuous set. Continuous set. It could be, for example, R again. So you can look at R to the R. In other words, functions that take real numbers and spit out real numbers. And then you can define the Borel sigma algebra on functions. And you can ask yourself, what's the probability that a function does this, a function does that, and so on and so on. Now here you need a little bit of restrictions regarding continuity of the functions. Again, I'm not going to go into much details, but let me just mention Cadillac functions. Which means continuous from the right and have left limits kind of functions. There are some restrictions which you need to make here. Not all functions will be allowed to build up a sigma algebra like this, but again, a wide class of functions can be included, and it's very useful to look at processes, for example, Brownian motion and the like.